Let us begin with a simple unease. Quantum physics works astonishingly well, yet it describes a world that stubbornly resists common sense. Consciousness, meanwhile, is the most immediate feature of our existence, yet it slips through every scientific net we cast. Theology, finally, speaks of meaning and origin in a language that seems orthogonal to equations and experiments. The controversy arises when one dares to suggest that these three domains, quantum theory, conscious experience, and the idea of God, might not be neatly separable chapters but different projections of a deeper structure of reality. Quantum theory tells us that the world is not built from definite facts alone. Instead, it offers a mathematical object, the wave function, that evolves smoothly and deterministically until, at some ill-defined moment, it does not. At that moment, possibility hardens into actuality. Physicists often sidestep this awkward transition by invoking observers, measurements, or entire branching universes. Yet none of these maneuvers truly explain how a single, definite experience arises from a superposition of alternatives. The formalism works, the understanding lags behind. Now consider consciousness. It is tempting to treat it as a mere byproduct of computation, an elaborate illusion generated by sufficiently complex neural circuitry. But this temptation rests on an assumption that all physical processes are, at bottom, computational. Quantum physics already undermines this assumption. There are aspects of quantum behavior, particularly those involving non-computable numbers and subtle global structures, that resist reduction to algorithmic steps. If the physical world itself is not fully computable, why should consciousness, which is rooted in that world, be so easily captured by computation alone? Here the controversial suggestion enters. Perhaps consciousness depends on physical processes that lie precisely at the border where quantum theory fails to give a complete story. In such a view, conscious moments are not passive readings of a finished physical script, but active participants in the resolution of quantum possibilities. This does not mean that minds arbitrarily collapse wave functions at will. Rather, it suggests that certain organized physical systems may be sensitive to objective, non-random features of quantum state reduction, features not yet encoded in our current theories. This idea unsettles many scientists, and rightly so. It challenges the comforting notion that physics is already conceptually complete, awaiting only technical refinements. It also challenges a popular picture of the mind as a programmable machine. But scientific progress has rarely advanced by preserving comfort. It advances when anomalies are taken seriously, not explained away. Where then does God enter this picture? Not as a supernatural tinkerer intervening in laboratory experiments, nor as a gap filler invoked whenever equations run dry. Instead, think of God as a hypothesis about the ultimate intelligibility of the universe. Mathematics has an uncanny effectiveness in describing the physical world, an effectiveness that borders on the mysterious. The deep structures of reality appear not chaotic, but profoundly ordered, even elegant. One may reasonably ask why such order exists at all. If consciousness is tied to fundamental features of reality, rather than perched precariously atop them, then meaning is not an accidental afterthought of cosmic history. It is woven into the fabric of the universe. In this sense, God is not an object within the universe, but a way of speaking about the source of its rational structure and experiential depth. This is not a God of dogma, but a God of coherence, a principle that underwrites both mathematical truth and conscious understanding. Critics often object that such ideas blur the line between science and metaphysics. Yet that line has never been as sharp as we pretend. Quantum theory itself was born from metaphysical discomfort with classical assumptions. To ask whether consciousness points beyond current physics is not to abandon science, but to extend its reach. The controversy, then, is not about inserting mysticism into physics, but about acknowledging that our best theories may still be incomplete at the most profound level. If the universe is structured in a way that allows conscious beings to grasp its mathematical essence, that fact demands explanation. Whether one chooses to call the ultimate ground of this structure God is partly a matter of language. What matters is the recognition that mind, matter, and meaning may share a common origin. In confronting this possibility, we are reminded that humility is as important as precision. The universe has surprised us before, and it may do so again, especially when we dare to ask not only how the world behaves, but why it is intelligible to minds like ours at all. Quantum theory stands as one of the most successful scientific frameworks ever devised. Its predictions have been confirmed to extraordinary precision, often to many decimal places, and its applications underpin much of modern technology. Yet, beneath this triumph lies a profound conceptual tension. The theory provides a set of mathematical rules that work impeccably, while remaining strangely silent about what those rules truly say about reality itself. This tension becomes most apparent when one examines the nature of quantum states and the role they play in describing the physical world. At the heart of quantum theory lies the wave function, a mathematical entity that evolves smoothly and deterministically according to well-defined equations. This evolution is continuous, elegant, and entirely precise. However, when a measurement is made, the same theory demands a sudden and discontinuous change. A range of possible outcomes, previously coexisting in a superposition, is replaced by a single definite result. The theory offers no clear physical account of how or why this transition occurs. Instead, it introduces a pragmatic rule that simply tells us what probabilities to assign to outcomes, without explaining the underlying process. Attempts to resolve this difficulty have multiplied over the decades. Some interpretations insist that the wave function never collapses at all, proposing instead that all possible outcomes occur in separate, branching realities. Others place the observer at the center, suggesting that measurement itself has a special status that defies ordinary physical description. Still others modify the mathematics to force collapses to occur spontaneously. Each approach preserves the predictive success of the theory, yet none commands universal agreement, precisely because the problem they address is not merely technical but conceptual. The difficulty arises from a mismatch between the mathematical formalism and our expectation of a single objective world. The equations describe a spread of possibilities, while our experience delivers one concrete actuality. The transition from possibility to fact is not something the theory describes in physical terms. Instead, it is patched in by interpretative rules that sit uneasily alongside the otherwise seamless mathematics. This uneasy coexistence suggests that the theory, for all its success, may not be the final word on the nature of physical reality. What makes this situation especially striking is that classical physics did not suffer from this ambiguity. In classical theories, the mathematics describes a world that simply exists in a definite state at all times. Probability enters only as a reflection of ignorance, not as a fundamental feature of reality. Quantum theory, by contrast, elevates probability to an intrinsic role, yet leaves unanswered the question of how probabilities give rise to actual events. The remarkable effectiveness of quantum theory, therefore, conceals a deeper problem. We possess equations of astonishing power, but lack a coherent picture of what they describe. This gap between calculation and comprehension is not a minor philosophical quibble. It strikes at the core of what it means for a physical theory to explain the world. The success of the formalism should not blind us to the fact that its conceptual foundations remain unsettled, pointing toward the possibility that a deeper, more complete framework still awaits discovery. The claim that consciousness is nothing more than computation has become a convenient assumption in much of contemporary science. Brains, on this view, are essentially biological machines, and mental life emerges automatically once information is processed with sufficient speed and complexity. This perspective gains plausibility from the success of computers and artificial intelligence, yet it rests on a hidden premise that all physical processes can ultimately be captured by algorithmic rules. The difficulty is that modern physics itself gives us reason to doubt this premise. Computation, in the strict sense, is governed by formal systems that operate through discrete, well-defined steps. A computational process can be simulated by a machine that follows explicit rules, no matter how complicated those rules may be. If the brain is purely computational, then every conscious experience should, in principle, be reproducible by an appropriate program. Subjective awareness would then be an emergent illusion, arising from the manipulation of symbols rather than from any fundamentally new physical principle. However, quantum physics already challenges the idea that nature is fully describable in algorithmic terms. Certain features of quantum systems involve continuous mathematical structures and non-computable numbers that cannot be reduced to finite procedures. Moreover, the problem of quantum state reduction introduces elements that appear to escape deterministic computation altogether. If the physical world itself contains processes that are not fully computable, then the assumption that consciousness must be computational becomes far less secure. There is also a deeper issue concerning understanding itself. Human mathematical insight, for example, often involves recognizing the truth of a statement without following a step-by-step algorithm. One can grasp why a proposition must be true even when no formal proof procedure is available that would compel a machine to reach the same conclusion. This suggests that human understanding may access aspects of truth that transcend mechanical symbol manipulation. If so, then consciousness cannot be equated with computation alone, no matter how elaborate the computation. Neuroscience, for all its successes, has yet to identify a clear mechanism by which subjective experience arises from neural activity. Correlations between brain states and conscious states are abundant, but correlation is not explanation. To say that consciousness is produced by computation is to redescribe the problem, not to solve it. The essential mystery remains: how physical processes give rise to the qualitative feel of experience, the sense of what it is like to be a conscious being. If consciousness depends on physical processes that are not computationally simulable, then attempts to reproduce it purely through artificial systems may face fundamental limitations. This does not deny the power of machines, nor does it diminish the importance of neuroscience or computer science. It simply suggests that the mind may draw upon deeper features of physical law than those captured by algorithms. The appeal of the computational view lies in its apparent simplicity and its compatibility with existing technology. Yet simplicity should not be confused with truth. The history of science teaches that reality often resists our most convenient models. To take consciousness seriously may require us to accept that it is rooted in aspects of the physical world that lie beyond computation, hinting at a level of organization and lawfulness that our current frameworks have yet to fully articulate. The suggestion that consciousness may be linked to unresolved quantum processes arises naturally once we acknowledge the limits of both neuroscience and quantum theory. While the brain is often described in classical terms, it is ultimately composed of quantum constituents, and its activity depends on physical processes occurring at scales where quantum effects cannot be entirely ignored. The usual assumption is that such effects are washed out by noise and temperature, leaving only classical behavior relevant to cognition. Yet this assumption is not a demonstrated fact, but a working convenience. Quantum theory, as currently formulated, contains an unresolved tension between its smooth mathematical evolution and the abrupt appearance of definite out-C ohms. This unresolved feature may not be an incidental flaw, but a clue pointing toward deeper physical principles. If state reduction is an objective process, rather than a mere artifact of observation or knowledge, then it could possess structure and regularity not yet captured by existing equations. Such structure might, in principle, interact with highly organized physical systems in a distinctive way. Conscious systems are not arbitrary collections of matter. They are extraordinarily organized, finely tuned, and dynamically coherent across many scales. It is not unreasonable to ask whether such systems could be sensitive to subtle physical effects that simpler systems would not register. If certain quantum processes occur at a threshold where classical description fails, then organized biological structures might be uniquely positioned to engage with them. Conscious moments, in this view, would correspond not to continuous computation, but to discrete physical events tied to the resolution of quantum possibilities. This perspective does not imply that consciousness floats free of biology or ignores neural mechanisms. On the contrary, It places biology at the center of the mystery, suggesting that evolution may have exploited deep physical features of the universe long before human theory caught up with them. Natural selection does not require understanding. It requires only that a process works. If quantum-sensitive mechanisms confer even a small adaptive advantage, their persistence would not be surprising. The idea is controversial because it resists easy testing and sits uneasily with prevailing paradigms. Many physicists prefer interpretations of quantum theory that preserve linearity and avoid introducing new physical processes. Many neuroscientists, meanwhile, are reluctant to invoke physics beyond established models. Yet history shows that resistance often accompanies proposals that challenge foundational assumptions. Importantly, this approach does not grant consciousness magical powers over matter. It does not suggest that minds arbitrarily dictate physical outcomes. Instead, it proposes that consciousness is associated with lawful, objective processes that are part of nature itself, though not yet fully understood. The role of the mind would be participatory, rather than causal in a classical sense, aligning experience with physical events rather than commanding them. If conscious experience is tied to such fundamental processes, then it cannot be entirely explained by higher-level descriptions alone. Neural activity would remain essential but not sufficient. The deepest explanation would lie at the interface where quantum indeterminacy gives way to definite reality, a boundary that physics has not yet fully mapped. Exploring this possibility demands intellectual courage, because it forces us to admit that our most successful theories may still be incomplete at the very point where mind and matter intersect. The traditional picture of the mind in science casts consciousness as a spectator, passively observing a world that unfolds according to fixed physical laws. In this view, reality is complete in itself, and experience merely records what has already occurred. Yet quantum physics unsettles this picture by refusing to describe the world as a collection of definite facts prior to interaction. Instead, it presents a landscape of possibilities that only later crystallize into actual events. This shift invites a reconsideration of the role consciousness might play in the unfolding of reality. In quantum theory, physical systems are described by superpositions, mathematical combinations of mutually exclusive states. These superpositions evolve predictably, yet they do not correspond to a single concrete reality. The transition from this abstract multiplicity to one actual outcome remains the most puzzling aspect of the theory. Standard approaches either delegate this transition to measurement devices or dissolve it into a proliferation of unseen worlds. Both strategies preserve calculation, but they leave unanswered why experience is always singular and definite. If consciousness were merely a passive witness, its definiteness would be a curious coincidence. One would expect experience to mirror the underlying multiplicity described by the equations, yet it never does. Each moment of awareness presents a single coherent world, not a blur of alternatives. This fact suggests that consciousness may be tied to the very process by which quantum possibilities are resolved, rather than standing outside it as a detached observer. To say that the mind participates in reality does not mean that it creates the world by force of will. Participation here implies alignment with lawful physical processes that convert potentiality into actuality. Conscious experience would then be inseparable from these processes, arising simultaneously with them. The mind would not intervene from outside physics, but would be embedded within its deepest workings. Such a view challenges the sharp separation, often drawn between subject and object. If experience and physical events are two aspects of the same underlying process, then the observer is no longer external to the observed. This does not collapse reality into solipsism, nor does it elevate consciousness to a supernatural status. It simply recognizes that the framework we use to describe the universe must account for the existence of experience as a real feature, not as an afterthought. The participatory role of consciousness also reframes the meaning of observation. Observation is not merely the acquisition of information, but a physical event with ontological significance. Each act of awareness corresponds to a moment in which the world takes on a definite form. The continuity of experience, then, reflects a sequence of such events, stitched together by memory and neural structure. This perspective is unsettling because it resists reduction to familiar categories. It cannot be fully captured by classical causation, nor by purely computational models. Yet it resonates with the lesson that quantum theory has been hinting at for over a century, that reality is not a static stage on which events play out, but an active process in which structure and fact emerge together. To take consciousness seriously may require accepting that the universe is not complete without the experiences that occur within it, and that mind and world are entwined at a level deeper than our customary descriptions allow. When the idea of God enters a discussion shaped by physics and consciousness, it often provokes immediate resistance. This resistance usually stems from a picture of God as an ad hoc explanation, invoked only where scientific understanding falters. Such a picture places divinity in competition with science, as though the advance of equations must inevitably displace belief. Yet this framing misses a more subtle and historically grounded possibility, that God refers not to an intervention within the universe, but to the reason the universe is intelligible at all. One of the most striking features of the physical world is its deep mathematical order. Abstract structures developed by the human mind, often without any practical motivation, later turn out to describe nature with uncanny precision. This effectiveness of mathematics is not logically necessary. The universe could have been chaotic, opaque, or resistant to coherent description. Instead, it exhibits patterns of great subtlety and elegance, inviting understanding rather than defying it. The question of why this should be so lies beyond the reach of physics alone. If consciousness is genuinely rooted in fundamental physical processes, then understanding is not a superficial byproduct of matter, but something intimately connected to the structure of reality. Minds are capable of grasping mathematical truths, discerning order, and recognizing meaning. This correspondence between the rational structure of the universe and the rational capacities of conscious beings demands explanation. It is here that the idea of God takes on a different character, not as a competing cause among causes, but as the ground of coherence itself. In this view, God is not an object located somewhere in space or time, nor a mechanism that tweaks quantum outcomes. Rather, God represents the underlying unity that gives rise to both physical law and conscious insight. The Arbius of physics describe regularities within the universe, but they do not explain why those laws exist, nor why they are expressible in mathematical form. To speak of God is to address this deeper level of explanation where questions of origin, order, and meaning converge. Such an understanding avoids the trap of invoking divinity to fill gaps in current knowledge. Gaps close as science progresses, but the question of why there is a lawful, intelligible universe in the first place does not disappear with improved equations. Instead, it becomes sharper. The more deeply we understand the structure of reality, the more remarkable its coherence appears. This approach also reframes the relationship between faith and reason. Belief in God need not conflict with rigorous science. It can arise from taking science seriously enough to ask foundational questions. The existence of conscious beings capable of understanding the universe is not an incidental curiosity, but a central fact in need of interpretation. When God is conceived as the source of intelligibility rather than a supernatural intruder, the divide between physics, consciousness, and meaning becomes less rigid. Reality appears as a unified whole, in which mathematical order, physical existence, and conscious awareness are different expressions of a single underlying principle. This does not resolve all mysteries, nor does it compel belief. It simply offers a way of thinking in which the presence of meaning in the universe is not an embarrassment to science, but one of its deepest clues. Scientific progress is often portrayed as a smooth accumulation of facts, guided by ever more refined techniques and increasingly precise measurements. In reality, the deepest advances have rarely followed such a tidy path. They have emerged instead from moments of conceptual crisis, when existing theories, despite their empirical success, revealed internal tensions that could not be ignored. These tensions are not signs of failure, but signals that a framework has reached the limits of its explanatory power. Quantum theory itself is a product of such a crisis. Classical physics worked extraordinarily well within its domain, yet it failed catastrophically when applied to atomic phenomena. The response was not to abandon science, but to rethink its foundational assumptions. The resulting theory was mathematically radical and conceptually unsettling, forcing physicists to relinquish deeply held intuitions about determinism and locality. Progress came not from preserving comfort, but from confronting the anomalies head-on. The unresolved problems at the heart of modern physics occupy a similar role today. The measurement problem, the nature of quantum state reduction, and the relationship between physical law and conscious experience are often treated as philosophical distractions rather than scientific challenges. This dismissal is understandable, given the practical success of existing models, yet success can breed complacency. A theory that predicts outcomes correctly may still fail to explain what reality